This paper delves into the complexities of function families in machine learning, focusing on the development of generalization bounds for regression and classification tasks. The primary focus is on the generalization error, which is the expected test error that compares the outputs between an unknown target function and a hypothesis function derived from training data. The paper explores various techniques such as covering number, packing number, growth functions, Rademacher's complexity, and VC dimensions to understand these complexities. The study's contributions include the use of geometric parameters gamma s to characterize generalization errors for both regression and classification tasks. For learning regression function f with Lipschitz constant kf using machine m with Lipschitz constant km, the bound is kf plus km gamma s. For one hot classification function f with classification boundary partial differential f, the bound is gamma s caret d1 volume b d1 0 1 partial differential f, where d is the dimension of the input domain. Partial differential f denotes the length of partial differential f, and volume bd1 0 1 denotes the volume of unit d1 ball. The analysis also establishes a relationship between the parameter value gamma s and the number of network parameters. Specifically, it is found that gamma s is inversely proportional to a polynomial of the parameter count of a network. The polynomial's order varies depending on the algorithm and network architecture. This outcome aligns with the understanding that increasing the network's layers leads to a larger parameter count, resulting in a smaller value of gamma s due to the refinement of the network's input domain. Building on this analysis, the paper has developed a deep neural network with gamma s is less than or equal to 1, WL, where WL represents the parameters of a network of layer L. In conclusion, this paper provides a comprehensive examination of generalization bounds for regression and classification tasks, leveraging geometric parameters to understand the relationship between network size and generalization errors. The findings underscore the advantages of over-parameterization in minimizing generalization errors and emphasize the significance of local geometric regions within a network's input domain. The paper presents a comprehensive analysis of generalization bounds for deep neural networks, focusing on the regression and classification functions. The authors establish novel sample complexities for these functions, which are inversely proportional to a polynomial of the number of parameters in the network. The analysis is based on two assumptions about the density of the training data in the input domain. The first assumption, referred to as the assumption of densely covering, posits that the data is distributed densely enough to cover the input domain within a certain radius. The second assumption, known as the assumption of histogram approximation, assumes that enough training data is available for each covered area to allow for an accurate approximation of probability mass using a histogram distribution. By combining concentration inequalities, the authors derive the generalization bounds for regression and classification functions, along with their corresponding sample complexities. The results show that the sample complexity for the regression function is O(1) delta O caret D, whereas for the classification function, it is O(1) delta O caret D1. The paper also reviews previous research on bounding generalization errors, highlighting the importance of understanding the fundamental properties of deep neural networks. The authors discuss various approaches to generalization bounds, including VC dimension analysis, Rademacher complexity, and Pack-Bayesian bounds. They also mention recent research on incorporating scale-sensitive bounds, which consider the margin concept, and the impact of implicit regularization of stochastic gradient descent on generalization errors. The author's approach emphasizes the importance of considering the local geometric structure of the input domain and the role of covering numbers in determining the generalization bound. They demonstrate that by making specific assumptions about the distribution of training points within local regions, they can determine the generalization bound without knowing the input density function. Overall, the paper provides a significant contribution to the understanding of generalization bounds for deep neural networks and has important implications for the design of neural network architectures and training algorithms. The research discusses the generalization error bounds for regression networks with Lipschitz continuity and one-hot classification networks. For regression networks, the target function is assumed to be Lipschitz continuous with a Lipschitz constant kf. The learning algorithm works on input distribution, x, f, x, defined as BD, 0, 1, times RL-valued regression pairs. The network M is a continuous function of Lipschitz constant Km, derived from gamma S dense distributed training data. The error between f, x, and m, x, can be bounded by the distance between the input point and training input x. The analysis relies on the assumption of densely covering the unit d ball and histogram approximation. The bound on the generalization error is given by equation 9. For one-hot classification networks, the classifiers partition the input domain into a finite number of regions, each assigned to a class. The 0/1 error function is used to compute the error. The research establishes a bound on the generalization error for both types of networks, demonstrating the importance of the Lipschitz constants and the assumptions made. The paper discusses the concept of a one-hot classification network, which is a neural network that divides the input domain into non-overlapping regions, each with a specific class. The classifier function f and the network M are both piecewise constant, meaning they assign each region a distinct class. The generalization error of learning the classifier function f using M is bounded by the sum of two terms: the average error between f and m on the training data, and the volume of a d-tube with a radius of gamma s, the smallest enclosing radius of the classification regions derived by m, multiplied by the size of the classification boundary induced by f. To calculate the generalization error, the paper introduces the concept of an affirmative parameter a to f, x, representing the maximum radius of a ball centered at x such that f, y, equals f, x, for all y belonging to the ball. The paper also defines a function hf, x, bar dblx minus y, bar bl2, that is non-decreasing and has a value of 1 if the distance between x and y is greater than a to f, x, and 0 otherwise. The probability mass that contributes to the generalization error is bounded by the volume of points within a distance no greater than gamma s from the classification boundary of f. This volume is calculated as the product of the volume of a d-1 ball with radius gamma s and the length of the classification boundary, partial differential f. The paper then uses these concepts to derive a generalization bound for a one-hot classification network, which is given in lemma 2. This bound states that the generalization error is less than or equal to the average error between f and m on the training data, plus the volume of a d-tube with radius gamma s multiplied by the size of the classification boundary, partial differential f, where p is the density over the unit d ball. The bound holds regardless of the density p over the unit d ball. The research focuses on establishing a connection between the generalization bound and the number of parameters in a network. It explores how the number of parameters affects the network's ability to cover the d-dimensional unit balls with a desired radius. The study introduces the concept of an oracle process to recursively decrease the enclosing radius to a desired value, gamma s. This process is linked to the number of parameters, demonstrating an inverse relation between gamma s and the number of parameters. The analysis also delves into the concentration bound and sample complexity with fixed radius random balls, aiming to find the concentration parameters and sample complexity. The uniform probability lower bound assumption is crucial in these derivations. The research provides a comprehensive framework for understanding how network parameters influence generalization error and sample complexity in regression and classification tasks. Here is a combined summary of pages 11 and 12 of the research paper. The authors establish a limitation for the densely covering assumption in EQ 27, outlining the conditions under which applying this assumption to generalization error is valid. This limitation is based on the likelihood that the first m balls, with centers sampled according to the density function p, will cover the input domain. To investigate the assumption of histogram approximation, the authors analyze the distribution of points in the training set S within each covering ball. They define a random variable zeme p to represent the histogram mass over bin p and calculate the mass concentration for each bin. The histogram mass over bin p is the average observation number in the sequence within the bin, given by EQ 28. By applying Hwang's inequality to the sum of independent random variables, the authors obtain the inequality in EQ 31. They then utilize the information from EQ 4, and 28, to derive the expression in EQ. 32. By setting the precision parameter Tp as P's op, they can represent the inequality as EQ. 33. Simplifying the inequality by assuming the range of the regression loss is within 0, 1, the authors obtain the upper bound in EQ. 34. Which is independent of P. They then consider the conjunction of the concentration bound for all P element of P's, deriving the concentration inequality for P's in EQ. 35. By considering the inequality where K equals Kf plus Km, gamma S, the authors obtain EQ. 36. Which is equivalent to the probability of obtaining the concentration inequality for the assumptions of densely covering and histogram approximation. The probability of confidence for S to satisfy the statements in EQs. 27 and 36 is determined using a precise parameter epsilon, which takes values within the range of 0, 1. The authors introduce a bound on the enclosing radius with gamma S less than 1/2 Kf plus Km, and establish a uniform bound for the confidence parameter delta, independent of S. Using the bound for delta 1, m, in EQ. 26. The authors obtain delta S less than delta less than 1, which gives a constraint on delta and epsilon. The requirement of delta less than 1 provides a constraint on m, which is m greater than m0 equals 1, c gamma ds. Delta minus express minus epsilon squared, 2, greater than 1, c gamma ds. 1 minus express minus epsilon squared, 2. The values epsilon, delta, and m0 obtained from m, gamma s, and their constraints allow us to establish the concentration bound for regression functions. Here is a combined summary of pages 13 and 14. The authors present a theoretical analysis of the generalization bounds for regression and classification functions learned by neural networks. They establish a theorem, Theorem 5, that provides a generalization bound for regression networks, which depends on the Lipschitz constants of the target function in the network, as well as the number of parameters and samples. The bound is expressed in terms of the probability of achieving a precision bound of epsilon, and the authors show that the sample complexity is of order O, 1, epsilon caret d delta, where d is the dimension of the input domain. The authors then extend their analysis to classification functions, deriving separate concentration bounds for densely covering assumptions and histogram approximations. They introduce a new theorem, Theorem 7, that provides a generalization bound for one-hot classification networks, which depends on the number of parameters, samples, and the probability mass of the target function. The bound is expressed in terms of the probability of achieving a precision bound of epsilon, and the authors show that the sample complexity is of order O, 1, epsilon caret d1, delta. The authors also provide corollaries to both theorems, which provide explicit expressions for the sample complexity in terms of the known constants and parameters. They highlight the significance of their results, which demonstrate that the sample complexity of a given function is dependent on the dimension of the input domain, the number of parameters, and the probability mass of the target function. Throughout the analysis, the authors make use of various mathematical concepts, including Lipschitz constants, concentration bounds, and probability theory. They also draw inspiration from previous work on random covering and provide references to relevant literature. The authors' results have important implications for understanding the effectiveness of learning algorithms and the amount of data required to achieve a specific level of performance. Here is a combined summary of pages 15 and 16. The authors present a lemma that assumes a uniform probability lower bound and derives an upper bound for the average number of random balls required to cover a unit D ball for the first time. The proof involves calculating the probability of a randomly chosen ball not containing a point x in the ball BD, x, gamma s, and then computing the expected number of random balls required to cover x for the first time. The result is E, xmin, is less than or equal to 1, c gamma ds, where c is the uniform probability lower bound parameter. The authors note that this upper bound is quite conservative and can be improved by considering a uniform input probability distribution, which leads to E, xmin, equals 1, gamma ds. They also discuss the importance of whitening images as a preprocessing technique to eliminate correlated components and establish an equalized distribution in all directions. The authors then explore methods to derive functions within the hypothesis space to achieve an oracle process that reduces the enclosing radius of the balls by at least half of their original sizes. They propose using a deep neural network, DNN, with L layers, structured as M0L equals, rho ML, ring operator, rho ML1, ring operator, rho M1, where ML represents an affine linear mapping, and rho denotes the rectified linear unit, ReLU, activation function. The authors analyze the properties of the DNN, particularly its capability for function approximations, and discuss the concept of input domain partitioning, where each partitioning region creates a polytope, an affine linear mapping domain. They also note that the refinement of partitioning regions in P0L sets up a tree-like partitioning of P0L, where each region in P0L plus 1 has a unique parent region in P0L. Finally, the authors propose an algorithm to partition a polytope and reduce the diameters of the resulting subpolytopes to a constant fraction of the original value. The algorithm uses hyperplanes passing through anchor points to make multiple cuts in the original polytope and create subpolytopes, ensuring that the diameter of the refined partition is at most half the diameter of the original polytope. The research paper presents a novel approach to partitioning convex polytopes using hyperplane cuttings, leading to a binary tree structure. The anchor point of a polytope is defined as the center of the maximum inscribed ellipsoid, which can be calculated using convex optimization methods. The volume reduction property is demonstrated by the inequality volume, Q, is less than or equal to 1 d, volume, P, where Q is a subpolytope of P. This property ensures that the volume of a subpolytope retains a constant fraction of its parent polygon. The paper also introduces the concept of the inner and outer ellipsoids of a polytope, which are used to approximate the polytope volume from the inside and outside, respectively. The inequality zeta d eta d is less than or equal to volume, qk, is less than or equal to 1 d, k volume, p, is derived, which implies that the sequence of radii of the principal axes of the maximum volume inscribed ellipsoid of qk decreases to 0 as k increases. The authors then discuss the construction of a binary tree of depth k, where each node is associated with a hyperplane, and the total number of parameters needed to reduce the enclosing radius of p to half its original value is approximately 2k, d plus 1. The number of parameters in the construction of P0L plus 1 from P0L is d plus 1, 2L beta, where beta is the maximum value of Kp for p element of P0L. The paper finally remarks on the construction of the affine linear mapping ML plus 1, which is obtained by stacking the arrays of hyperplanes generated by cutting each partitioning polytope in P0L. The authors also discuss the implications of their analysis on sample size efficiency and benign overfitting in regression and classification functions. Here is a combined summary of pages 19 and 20 of the research paper. The authors analyze the sample size efficiency of learning regression and classification tasks, demonstrating that learning classification tasks requires fewer samples than regression tasks to achieve a desired level of consistency. This is attributed to the difference in sample complexity, as shown in corollaries 6 and 8. The study suggests that bounding the prior information kf and partial differential f, rather than their precise values, can improve sampling complexity and achieve a higher sample complexity. The authors also explore the phenomenon of benign overfitting, where deep neural networks can achieve remarkably low test errors while interpolating the training data. This challenges the traditional belief that a slight empirical error bias in a learning model will inevitably lead to significant prediction variance, resulting in overfitting. The study reveals that over-parameterization models and densely arranged training data can lead to benign overfitting, a highly desirable outcome. The equations 9 and 19 contain a term that limits the difference between generalization and empirical errors, known as overfitting. The choice of input data density function is not critical, but rather the availability of ample training data points is crucial. The overfitting term is proportional to gamma s in regression, whereas in classification, it is proportional to gamma d-1s. This makes it easier to achieve benign overfitting in classification learning than in regression. The authors assume that every covering ball within the input domain needs to encompass at least one training point and an adequate number of training points, which is crucial in preventing overfitting in a classification system. This assumption is particularly relevant when considering the observed overfitting in the tree hypothesis class, where each partitioning region of a classification tree consists of precisely one training point. Finally, the authors discuss shallow versus deep neural networks for learning Lipschitz functions, highlighting that deep neural networks can effectively represent a target function with hierarchical and compositional structures using fewer parameters than shallow networks. This can lead to lower generalization errors, as demonstrated in the PAC analysis with finite hypothesis space. Deep neural networks can partition the input space into exponentially more regions than their shallow counterparts, resulting in smaller generalization errors. The analysis explores the benefits of deep neural networks by examining the Lipschitz constants of their building modules. It demonstrates how deep networks can generate functions with smaller Lipschitz constants, enhancing generalization error for regression functions. This understanding is crucial for developing networks with smaller Lipschitz constants. The expected number of balls covering a continuous density function is also discussed, providing a bound for the minimum expected value of E, X-min, by leveraging the approximation of continuous functions using piecewise constant functions. The inductive bias related to over-parameterized systems is acknowledged, highlighting the importance of constraints on the norm of weight coefficients for regression and the focus on the classification boundary for classification. The summary concludes by mentioning the need for efficient algorithms linking covering geometry and network architecture, as well as further investigation into sample complexity for generative models. The research discusses the application of geometric-related parameters for density estimation, building upon diffusion generative models. It explores the potential of using the geometrically adaptive construction approach as a basis for generative models and compares them using sample complexity measures. The authors draw from various theories, including machine learning foundations, neural network learning, and statistical concepts. They also reference works on VC dimension, pseudo-dimension, and margin bounds for neural networks. The study aims to reconcile modern machine learning practices with the classical bias-variance trade-off. It emphasizes the importance of understanding generalization in deep learning, discussing stability, algorithmic regularization, and the role of over-parameterization. The authors also touch on data preprocessing and augmentation techniques, highlighting their significance in modern machine learning. Here is a combined summary of pages 25 and 26 of the research paper. The paper cites various works in convex optimization, geometrical algorithms, and combinatorial optimization, specifically referencing Fries and Teng's work on computing the diameter of a polytope, 32, and Barnett's upper bound for the diameter of a polytope, 33. The authors also draw from Boyd and Vandenberg's convex optimization, 34, and Grotschel, Lovish, and Shriver's geometrical algorithms and combinatorial optimization, 35. In the context of neural networks, the paper references Heo et al.'s meanfield behavior of neural tangent kernel for deep neural networks, 37, Hwang et al.'s work on why deep residual networks generalize better than deep feedforward networks from a neural tangent kernel perspective, 38, and Radhakrishnan et al.'s findings on wide and deep neural networks achieving consistency for classification, 39. The authors also cite Belkin et al.'s work on understanding deep learning through kernel learning, 40, Hastie et al.'s surprises in high-dimensional ridgeless least squares interpolation, 41, and Cao et al.'s benign overfitting in two-layer convolutional neural networks, 42. Furthermore, the paper references Masker et al.'s analysis of when and why deep networks are better than shallow ones, 43, and Montufar et al.'s work on the number of linear regions of deep neural networks, 44. The authors also draw from Sarah et al.'s bounding and counting linear regions of deep neural networks, 45, Masker and Poggio's deep versus shallow networks from an approximation theory perspective, 46, and Hwang's representation and decomposition of functions in DAGDNNS and structural network pruning, 47. In the realm of generative models, the paper references Song et al.'s score-based generative modeling through stochastic differential equations, 48, and Sol-Dickstein et al.'s deep unsupervised learning using non-equilibrium thermodynamics, 49. Finally, the authors cite Goodfellow et al.'s generative adversarial networks, 50, Arjavsky et al.'s Wasserstein generative adversarial networks, 51, and Kingma and Welling's auto-encoding variational Bayes, 52.